Hello, everyone. I hope you had a great break. So we're about to have a talk from Eleanor McHugh. Eleanor is an aficionado of both Go and Ruby, is the author of A Go Developer's Notebook, and is currently the Director of Innovative Identity Solutions. Now, last year at GopherCon, I had a bit of trouble with Eleanor because, sadly, her talks are a little bit too engaging for her own good. So if we're here in 3 hours' time and I'm sitting quite placidly with a big smile on my face in the front row, could someone just tap me on the shoulder to let me know that we're slightly past time? And then I'll ask her if she wouldn't mind stepping down for a little while. But until then, with her talk, A Gopher's Guide to NIX Plumbing, please give a big hand to Eleanor McHugh.
Good morning. All right. I really have no sodding idea how to start this talk. This all started in 2009. I mean, my involvement with Unix didn't start in 2009. That started in 1998 when I broke into my first, got legitimate access to my first little Ultrix box in the engineering department that I wasn't part of at Kingston University, which was then a polytechnic. Anyway, for a lot of years I was a systems programmer. By which I mean I was an embedded systems programmer for a decade, something that I harp on about all the time because, please God, pay people enough to do that work so I can go back. You only have to care about hardware and you don't have to care about business people very much. It's very nice. Anyway, in 2009, I was looking for an excuse to get to a Ruby conference in Manhattan. And I thought, what better way to get an excuse for that than to say, I'll come and talk to you about how to do kernel scripting in Ruby. This was the last time that I was on the Ruby conference circuit in any serious way, because I did 5 conferences, burnt myself out. Go released the day I came back from the last one of them, which was RuPi in Poznan in 2009. I took one look at it and went, it's got multiple returns. And there's history there, because for my MSc, I was not allowed to develop a language with multiple returns because I was doing a more business-oriented degree, and I had to do something more business-oriented. So I wrote an autopilot instead. Which I don't see how that's any better. So I thought this year, I've annoyed people with a lot of other stuff. Let's make the entire Go team go, God, no, don't do that. So that's what we're going to do. Now, I've only got 11 examples here. There were supposed to be more. It turns out that debugging things when you're using Syscalls and semaphores and things like that is a little bit of a pig. And I'm also building a cabin at the same time, so I'm a bit distracted. So we'll go where we go and see what we see. So, right, Unix is very old and venerable. It dates back to 1969. And you should recognize one of these two people. For here we have Ken Thompson and Dennis Ritchie, the two creators of Unix. And as Ken Thompson is one of the 3 creators of Go, and as Rob Pike is sort of like, before he became famous for doing stuff with languages, was famous for X Windows and Unix, it isn't really a surprise that Go is actually quite good at sitting on Unix. And we have a couple of books. Please don't try to learn PDP-11 assembly language, or its big brother, VAX-11 assembly language. They read like high-level languages. It will ruin you for assembly language programming. No, we can't go further than that. Obviously, everything I'm going to talk about is stuff that was invented in C originally, and we're not going to touch much C in this talk, but we will touch some. Yeah, Unix. It's got stuff. Not interested. I'm more interested in that bit. The whole point of Unix is to get out of your effing way and let you build the programs that you either need to build or want to build. It is not an operating system for business types who, since the invention of COBOL, have been inflicting processes on us. It's an operating system for hackers who like to write code, don't feel embarrassed writing code, and would really wish that everybody would sod off and let them drink their cup of tea and finish writing code. I'm one of those. The basic premise is quite simple. You build little things and you compose them and pump output from one into another and things happen. No, God, my poor clicker is dying. This has been to so many places with me. Now, I did have a sensible disclaimer slide. This only works on Go blah, 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 and only tested on MacBook Intel and all of that. But really, the truth of the matter is, don't do any of this. I'm going to show you stuff you shouldn't do unless you want to do it for fun. Don't do it in a production code base unless somebody pays you a lot of money and takes the responsibility for when it goes wrong. And we will get to things that will go wrong. Right. Let's start with something simple. So, the heart of Unix is that it's multitasking. And the point of multitasking is that you can have these discrete little processes that talk to each other. And one process does one little job, and it feeds some output to another process that takes it as input and does another little job. And you get these little pipelines that run between. So the first thing we really need to do is get a process. I mean, technically we've got one. The program we were actually in at the time is a process. But it's kind of nice if you can have other processes doing other things. So in this case, this is the highest level interface that Go gives us for all this malarkey. I am going to launch the echo program. It's going to echo hello Golang. I don't actually care what echo does from the point of view of writing the code. It's a command, and it takes some arguments on its commands line, and that's all that this is doing. This is pumping its OSArgs value. Right? I can grab hold of the output from that. Now, when I grab hold of the output, I'm not getting it interactively. I'm just sitting there and waiting until it's finished producing all of its output, and then it dumps it all at me effectively, at least from my perspective. Under the hood, it sort of trickles sending it on its standard output. But to me, I just get this big blob of output and I do something with. And all I'm going to do is print it. This is the very simplest program you can come up with to create a subprocess. Now, it's called a subprocess because everything in sodding computing is a tree. And processes all live in a tree. So this process that this program's running in, that's our parent process. And this over here, this is our child process that's gone off and done some work. OK. Now, there's a basic format to how I'm going to talk about stuff. I'm going to develop a DLL that means that I can make it very clear what's happening. And then I'm going to talk about bits of that DLL to explain how they work. I don't know if there's enough content here for an hour, or half an hour, or 45 minutes, because I only finished writing what's here about 45 minutes before I got in this morning. And there's a lot of examples that I just didn't have time to finish debugging. And I don't like showing off code if I've not debugged it. It should work straight from the slides, otherwise it's a bad talk. The constraints you put on yourself that make life more difficult. OK, so firstly, there's three things up here I'm actually interested in. I'm interested in being able to talk to the operating system. That lives in the OS package, which is part of the standard package library. I'm interested in doing that whole executing a subprocess thing. And I'm also interested in some specific, system-specific stuff that lives in Syscall. I'm going to use Syscall extensively, and then there's an alternative which is specific to Unix. Now, I keep reading things that say that Syscall has been deprecated, and I keep seeing other things that say, well, I'm not using the Syscall in Unix. I'm using this Syscall. I have no idea what's going on. I have no privileged insight whatsoever. I just have a command line, a text editor, and more time than I should be using. So our program here is going to launch off as many different commands as I give it on a command line. And you know what? I wasn't expecting to have an hour, so I'm actually going to go into a terminal. God, that light's bright. Go into a terminal and show you exactly what I mean. Which means doing that, and then doing that, and then being back there. Well, of course, now I can't actually see the slide, so that's not very helpful. 2. So, go, run. Oh yeah, this is also a really bad idea. Don't put lots of programs in the same directory and give each of them package main. It happens to be incredibly good for doing examples in talks. It's a dreadful idea if you ever want to build anything. So in this case, I'm going to go echo, let's see. I don't know if it's actually going to do path expansion, but we're going to ask it. And then we'll do an ls-al. Oh, and then, of course, there's the other bit. These examples all rely on a helpers file so I can get all of the bullshit out of the main code examples so you can just concentrate on what they're doing. And did we get an echo? Oh, bup, 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 bup. Not that I can see, but we did get an ls-al, so I'll count that as a win. I'm not greedy.
There is an echo.
There was an echo, brilliant. I can't actually see at any bloody distance because I'm too short-sighted for my glasses. I'm too long-sighted for when I'm close, and it's just, ugh. I really only normally live at terminal range, which is right here, so. Right, so our program is going to create a whole pile of subprocesses. This parallelized thing I'm going to talk about in a second. For each one of these parallelized tasks, we launch our command. To do that, I'm actually going to find out what my preferred shell variable is from the environment. I'm being kind. For people who want to use C shell or fish or any of the other mad shells that are out there. I mostly just live in Z shell these days because that's the one that comes straight out of the box in my Mac. I wish I was still in Bash. It's not as easy to write dodgy scripts in Z shell as Bash, but I suspect that's intentional. Down here, we're going to grab the standard out and the standard error that the operating system has provided to our main program, and we're going to let each of the commands that we launch off have those as its standard out and standard error. So it will dump any garbage straight to our terminal that gets spewed out if we type in a wrong command, so we can see it, and it will also dump the output straight to us. Welcome to our first syscall. This is a very polite wrapper to find out what the process ID of my current process is. That is not the process that's execed, that is this process here. And that's so that for each of these, I can say, well, I'm launching off this process over here, and this is my process ID. This c.string over here will print out a whole pile of stuff about the command, and that will include its process ID, I think. Either that was command line, can't remember. Doesn't matter. Then, over here, for every one of these shell commands, we're going to launch off a timer that's running in our main program that will kill it after 5 seconds. So it'll run for 5 seconds and then dead. In came the doctor, in came the nurse, in came the lady with the alligator purse. But it wasn't. It isn't necessarily guaranteed to be dead. It can become a zombie. There's all kinds of weird stuff that can happen on Unix. But anyway, the launch command is not very exciting. It's just, you know. So let's have a look at what we're doing. Now, parallelize is actually quite useful. It's not a nice little pattern. So we've got a standard package sync that includes this concept called a wait group. And wait groups are great. They're this little atomic thing that every time you start a task, you just tell it that you're starting a task by adding 1 to it. I don't like the naming of that, to be honest. I don't like the fact I can add 5. That just feels wrong for what it's actually doing. But I might do a timer example one day that just uses wait groups to do the timer. It'd be kind of funny. But down here, all I'm really doing is I'm saying, you've given me a piece of work. Oh, yeah, we're going to do a lot of function parsing. Hope you don't mind. This technically is a sequel to last year's talk on functional programming. Right. So I'm going to pass in a nice little function or closure of any type. Notice we have made it fully generic. And I'm just going to make sure that it runs off, does its bit of work, and then when it's finished, it decrements this wait group. So each time a task dies, the wait group counts down by 1 until all the tasks are done. Wait down here waits until all the tasks are done, and then we pop straight back out. It's a nice little bit of code, and I like the fact that you can write DLLs in Go, because a lot of people don't. And I'm old-fashioned. Is there anything else to say here? Oh, yes, obviously. Right. We're ranging over a loop. Whenever you're launching Go routines inside a loop, always make sure that whatever thing outside you want to use inside, you pass as a parameter. This loop goes around, God, I used to actually know a reasonable number, but let's say that takes 20 nanoseconds. This Go command here, from the time that it executes and says, OK, that's happening in the background, I'm just getting on with things, until this bloody thing actually executes, 400 nanoseconds? You walk through a lot of loop space in that time, and whatever the value of that n there is, if we're referencing that directly from here, that's the value you'll get. So if you've exhausted the whole of your loop count, you'll only get the last value. It's the most insanely annoying bug. And I've been bitten by it so many times that I go out of my way to avoid it. Now, this little example is slightly more complicated. And, oof. Let's go back and have a, no, backwards. Let's take this slowly. It's too early in the morning, 3 hours sleep doesn't help. Right, so here, now you are just trolling me, stop it. Right, so back here, we're launching off a command and we're setting up a whole pile of stuff here using exec.command. But that's a high-level approach to doing it. And what we, oh, now we're going the wrong way again. Oh, there we are. I'm not standing with you. I know, well, I'm not. Right, what we're going to do over here is we're going to go down a level of abstraction. We're actually going to go and start the process manually. Now, os.startProcess will take, let me see, I've jury-rigged together a command which consists of the command I want to do, a parameter to it, some more parameters to it. I'm using this -c because it felt right at the time. Don't hold it against me. But the main thing is, shell command is now taking a set of parameters up here, right, which it's getting in this function here, which is part of being parallel and being given one OS arg. So the first argument there comes into the first invocation of this function, and this here will then result in shell command down here getting one command to run, just one. And then it's going to want to grab a process and do something for that process. This builds our command line, of which we need the very first entry of that to be the name of the program. It's a fully path canonical name at that point. So that's what's actually going to run, to do our thing. That's where the shell runs. And then we give it the whole command line, because shells do expect to get the name of themselves as part of their command line args, right? This stuff is all a lot weirder than it needs to be now I think about it. We're then going to grab hold of a process ID for the program that's actually launching it, so we can print out a little logging message. All the way through, I am using log, not format, print, whatever, because that would go to standard output, and log will just go off to wherever log lives. It's probably better in a real-world program. When we start a process, we also have to give it a set of files. There's 3 that are basically by default given to every Unix process. Standard in, standard out, standard error. Each one of them gets a file descriptor, which is a number. It's an integer from 0 upwards. Every single process you look at, standard in will be 0 if it has a standard in, which it should have a standard in. I mean, I can't think why it wouldn't, but it might not. So here, we're going to create a set of standard in. We really are. Come on. We're going to give it a little set of 3 files. The standard in, the standard out, and the standard error for our process. We're going to say you use the same ones we're using. Shells do this all the time, so it seems perfectly reasonable to do that. I'm also going to wrap up this time after func, because I really don't want to have to keep typing the time.second everywhere when I want to set a timer. I know that I want to set timers for a number of seconds, so I just wrap things. It's kind of a talk on refactoring, I guess. Don't hold it against me. I promise never to tell you how you ought to write your code. There. Okay. Right. So down here, that set of 3 files, that's passed in as part of this thing called a proc attra. Now, that's a set of attributes that describe a process. When you create a process, you get a handle to one of these things, and you can look up stuff about it. And when you're creating a process this way, you create one of them to give to the thing that creates the process. We then just call our function that does our work, which gets our actual handle to our process, so we can kill the process up here because it knows about it. And then we just wait for the process to finish. So this is, you can use this to build a really, really inefficient version of semaphores, locks, mutexes, etc. Please don't build mutexes with processes. It's a horrible idea. But if you are going to do it, please go and do it on Windows. Now, let's get past that. Oh, God, time is going much quicker than I thought it would, so I'm going to speed up. OK, so for our next little example, I'm going to create a child process, and I'm going to interact with it not over standard I/O. I'm going to interact with it by sending it signals. Now, a signal is literally just an integer value that turns up at the process. The process doesn't know where it came from. It only knows what type it is. There's lots of amusement can be had with that concept outside the scope of today. And I'm going to set things up. So I'm going to wait 30 seconds before I kill the process that I'm running. I'm going to wait 20 seconds, so 2/3 as long, to send a sig term to the child process I'm going to create. So I'm going to kill my child before I die, right? Which is a bad practice. And then every second for 20 seconds, I'm going to send that process an interrupt signal. I'm going to run this one from the command line, because otherwise it makes no sense. This is the closest I'm ever getting to live coding. I refuse to go any further than this. Right, so that was 4, wasn't it? So we can get rid of the command line parameters. I don't think we need those. Oh, it'll be called parent. OK, I have naming conventions, and they're also kind of crap. Right, so I've got a parent process that is currently talking to a child process. It's sending the child process this interrupt signal once every second. Boom, boom, boom. This is the parent process. Log, I've set up log, so it will quite happily tell me about which process is doing what. So 11.172 is the parent, 11.173 is the child. The child does a whole pile of stuff, then it exits, and then the parent goes that the child is finished, and then it exits. Right? It's a very simple concept that's horrible to describe. So, going back to this. OK, so let's start with run program. So down here, I've just taken what we did in the previous example, setting up a command line, setting up some standard I/O. I've put it all in like that because otherwise the line just goes on forever if you do it in line, and it doesn't fit on a slide nicely. I've created a helper function, a set of helper functions, in fact, called logpdef in this case. This is a normal log call, but it finds out what the process ID of your process is. So it prints it out in the log. So you can therefore see which process is doing what. And this bit is just the same as we already had. We're doing our workload, and then we're waiting for it to finish. So if we skip on. These are really simple wrappers. The main thing that's important is they're all doing syscalls to get PID. Except for fatal. I seem to have forgotten to do it with fatal. There we are, bug. Found my first bug I can actually spot. Nothing very exciting about those. Something more interesting, though, is tickers. Now, a ticker ticks, and it does it based on duration. In this case, I'm saying tick every second. Operating systems have a finite minimum tick time without using... Well, real-time operating systems have high precision timers, and they can quite happily do very small ticks in T, down to the fractions of a millionth of a second. But commercial operating systems have this habit of having tick timers that are every millisecond. So ticking on a computer can be a strange thing. In this particular case, I don't really care about the detail. Go gives me a ticker. I give it a duration. I read off of the ticker because it exposes itself as a channel. And then I keep doing that forever, but I've got a countdown on my ticker. So when the countdown hits 0, I return and my ticker dies. In the meantime, you might want to run many different tickers at the same time, so I've put a sync wait group in. The wait group will tick up, the wait group will tick down. This means, as this is given back as a return value, that somewhere else in your program you can wait on all your tickers to end if you really want to. Because otherwise, some of your tickers might get cut off before they finish doing their job. So, boom, boom, boom. Oh, I've gone back in the opposite direction again. Right. Now, this is the child. This is the program that's going to be in our child process. This program is going to listen for signals. Right? So, we start that by creating a channel of signals, quite handily. I've buffered it at 1. It doesn't need to be buffered. For our purposes, it makes no difference because we're sending signals so slowly, once a second. But down here, you just range on that channel of incoming signals. And then if it happens to be a sig term, we will close the channel, which will then mean that we stop ranging on the channel, which will mean that we then exit the program. And when we exit the program, then obviously the parent process goes, program is ended. Right. If we get to that point. There isn't a lot really exciting to say about that. Anything else? I mean, obviously, you use a term to tell a program that it should terminate, but there's lots of signals for lots of different purposes, and there's also some user-defined ones that we'll use later that you can use for whatever you want. Deliberately listening for operating system-generated signals, unless you know what you're doing, is probably a bad idea. Suck it and see, sort of thing. Right. Oh, come on. Be obedient. Right, we've done every second. That's the child. Where are we now? All right. Program number 5 is kind of a variation on program number 4. And I've got to remember what kind of variation it is. Oh, yes. I've introduced a signal handler. I don't think I had that in the previous one, did I? Go back. No, I didn't have a signal handler in the previous one. So this one is going to exchange signals with its child. The child process is going to send a signal back in response to receiving a signal. So, ping, pong. Standard conventional, I want to test how concurrency works, sort of program. Nothing down here is particularly different. I've only actually continued to list one program because I have not moved it off into the helpers file. Because it's just, I don't know, maybe not. Probably should. Not that concerned. Right. So we've got a package for handling signals, os/signal. And all we have to do on a signal, this is great, because we receive a signal, right? And we've got a signal type that we want to look for. So we say, notify me when that signal happens, and do so on this channel, C. And then just go away and do some work until whenever. Now, obviously, in a real program, you'd have some guards around this to make sure this go routine stays alive, like I've done in other places and stuff. But it's such a stupid example, I couldn't really be asked. All we keep doing is just keep doing the job until the channel is exhausted. And then we exit. That's all a signal handler is. Oop. Come on. Back one. And that's literally the only change in that program, which is great. I can tick off 5 really quick. The child's got a slightly different job to do, though. The parent knows its children because it's created them. But the child doesn't know its parent until it asks. So in this particular case, we've got a syscall, ppid, that allows us to ask for our parent's process ID. And then we can find that process. You can put any random number in there, and if there's a process, you'll find it. Except on Unixes, you can put any random number in there, and even if there isn't a process, it will still give you back a process handle. So you can't just rely on that bit of information. You then have to go off and, to make sure it's really a live process, you have to send it a signal. And only if it receives a signal is it a live process. We'll get to that later. Right, so down here, I'm just in my child, I'm listening for interrupts and terms. When I get an interrupt, I'm going to send a signal back to the parent. Right? So this PP here, this is the process that I got for the parent ID. So I now know who my parent is, which is quite a wise thing to be able to say. And I can send it back the messages. At the other end, every incoming message signal it gets, the signal handler's going to handle. Right? There's not really much more to say about that. Right. What about if we've got a whole pile of child processes, and it's not so much that we want to signal them from the parent? What if we want them to signal each other? Effectively, we want them to go and play Ring a Ring of Roses or something like that, or Chinese whispers. That's actually quite annoying to arrange, because you can't just say, oh, by the way, signal all your siblings, because a process doesn't know its siblings. It only can get its parent. So what this program does is a little bit different. Firstly, I'm going to allow several children to run at the same time. So I've invented this stupid little method called... Actually, perhaps if we just stand that up. Perhaps it's just that my MacBook is getting in the way. Right, skip past... Oh, God. Now I'm lost in my own code. Right, we've got this thing up here, task list. It's really boring. All it's going to do is take a whole pile of strings and turn them into a slice of strings. And there's other ways I could have done it, and I didn't have to give it a name, and probably it's a dreadful name for what it's doing. But in the context of the example, it makes perfect sense as you read the example, which is part of the point of DSLs, is that the code you're reading on the screen should look as much like pseudocode as you can possibly make it while still executing. So in this case, I've got this T, which is a list of 3 calls, well, 306_child. And then down here, when I parallelize, I'm parallelizing across that list of 3 different things. I get 3 instances will run of the same program, right? And for each one of these, I run the program, boom, boom. I get a process that's associated with something, and an input and an output file. We'll get onto those in a second. I've then got this thing, C. This is my children. Every time a new program runs, I append its process ID to C. So I've now got a list of my children. I don't have a system call I can do this with. I have to build this list manually, so this is how I'm doing it. So if I've got 3 children running, I'll have 3 IDs in there, 1 for each process. For each one of them, I'm going to let them run for 10 seconds, and then I'm going to kill them, and then I'm going to kill their input file. Now, what we're playing with here are actually pipes. We're creating a pipe between a parent when it opens, or rather a parent, and the child that it opens. I use the input for sending signals, sending information down to the child, and I can send that in any form I want, because a pipe will take anything that could be text or binary format. The out is what's coming back from the child. And this is a 2-way communication that happens in real time. So I can say, I'm going to give you a message, and then I can get a message back, and then I can give it another message. So unlike what we had at the start, where we've got that whole dot output, and we're grabbing the entire output of the command, what we're actually doing here is we're just saying, I'd like a conversation, now I'm going to send you something, you send me something back. It's pretty much the same patterns we use when we do network coding. It's just now we're doing network coding directly between processes over a pipe. Down here, we've got a message loop. Now, what the message loop does is it just sits there. I've probably done input and output the wrong way around, but never mind. It just sits there on one of these 2 files. And every time something comes in on that file, we can do some work on the string that we get. And we'll go into how that's created in a minute. I'm going to log some crap out so I can see it happening. I'm going to build a list of peers as I'm going, so I can print out what the peers that I, as the parent, know about are for the particular process I'm talking to. I'm going to run this. It's 06 parent, isn't it? Boop, boop, boop. Oh, God. Boom. And I'm going to make the text size a little bigger. It occurs to me I keep my terminal text too small for people. There we are. Right, I've launched out 3 processes. I'll let it run for a bit, and then we'll talk about what we actually see. That was 6, wasn't it? Yes. Okay, so we've got some things going on here. We've got 4 process IDs actually in use in this, and I can get back to the top of the list like so. So, we've got our parent process, 11.247. Hello, 11.247. And 11.247 is going to launch 11.248, 249, and 250. It surprises me that those are sequential. Normally, people harden operating systems so that when they launch processes, they don't give you the next process ID as the ID of your spawned process. They normally randomize it somewhat, and I remember Macs randomizing this somewhat. And so I'm kind of surprised it's not randomizing them and they're all sequential. As an attacker, I can use that to gain all kinds of naughty compromising capabilities on a box. Right? So it's not very good. And when doing this yourself, yeah, something to think about. But each one of the children is going to send a hello message. Now, it can be anything. I could have put dog, I could have put Thursday, whatever. But I get a text message that comes up from the child, and then I can interpret that text message, and I can choose to do whatever I bloody want with that text message. But in this case, it's just hello to say, hi, I'm here. And then what I choose to do is build a list of the children. Those are the 3 processes. And for each one of those children, I can figure out a pair of children it can talk to. So this would be the peers for 11.248, because it's 11.249 and 11.250. I should probably put that in here, actually, in the debug log. And then down here, this is another pair of processes that can be talked to, and they're being talked to by 11.249, because that's the missing number. And these 2 can be talked to by 11.250, because that's the missing number. That's what peers is. It's just a way of showing that. I'll fix that at some point and make it more readable. I am giving versions of this in the future. I probably shouldn't, but I am. Then each of these processes can go off. Each of the children can send signals to each other because they know about each other. But they only know about each other because after they send this hello message, they get sent one of these pairs of peers that I know about. And if more processes come in while I'm running, I might well shove, don't do that. That was not friendly. It's kind of salty because it's a last generation Intel MacBook Pro. And it knows that Apple are going to make it completely unusable over the coming year to try and convince me to move across to... I've got a Mac Mini that's Apple Silicon, and it's fine as a server, but I just don't want it as a day-to-day machine. You know, I would actually be here with a 12-inch MacBook, except I couldn't bloody get enough of a connection in the hotel to be able to transfer the slides across. So, which is why I've got the big thing with me today. I don't normally have it. Right. Having shown you roughly what this does, let's get into the weeds. Boom. All right, firstly, run program. I've introduced this concept of try-wait down here. We'll meet that in a while. I don't really care about it. It's not very interesting, I think. Whoop. Peers is literally just producing a list of things, turning them into numbers and sending it off to the process that, you know, or getting it from a process. Try wait, oh yeah, if we can't wait on a process, then we can give an error message. Task list we've done. Drop tail is just a convenience so that I can do that rather than having to do that in there. Tokens is me just literally splitting a set of single string by spaces. Because we're only passing process IDs, they're going to be discrete integers. Put a gap in between, I've got a message protocol. I could write an RFC on that. It's not like the world doesn't have enough. This is more interesting. So now we're getting into how the 2 of them talk to each other to share this information. Send message is usable on anything that's an I/O writer. That's a file that's a pipe, or anything that implements a write method that just takes a slice of bytes as its parameter. I think it has to give back an error, but I can't remember. But anyway, one of the greatest bits of power in Go's package library is the number of I/O readers, I/O writers, and their related things. Because it means you can turn it. Where people mock things in other languages, you can just go, well, I quite like a string to actually behave the same way as a file. I'll just write a read and a write method for it. So in this case, I'm actually only interested in one thing, slices of bytes. Every time I get a slice of bytes, I'm going to stick a carriage return on the end, I'm going to pump it down the line, and I'm calling that a message. So my messaging format for talking between parent and child is discrete pieces of text separated by spaces indicate different messages in the stream, or rather, different words in the message. And then every time there's a carriage return, that was the end of that message. This is 1980s, I'm in BASIC territory, where a portion of my brain is going to forever live, unfortunately. Now, I can then do some slightly clever stuff. If I get a string, I can automatically convert it into a slice of bytes. If I get a rune, I can create a string from that rune, so I can send single characters and make sure they still get their carriage return. And if I've got a stringer, well, literally anything that turns up as a stringer, I can now send as a message with a carriage return on the end. So that's kind of neat. I could go further. I could put a gob down there, or I could put JSON down there, or whatever. And now I can send literally anything I want through the same send message function. I don't have to write separate send messages for that kind of thing. And if I can't do anything at all, then I can quite happily say, oh, well, I couldn't send that. By the way, this is the type of it. So you can go, do I not support that type? What would I have to do to support that type? So this is a dreadful insight into what I do at keyboards. This really is. Right, to go with a send message, we've also got a receive message. So I'll talk about that before the message loop. So for receive message, we use a reader. We just take anything that's an I/O reader. So that's anything that I can say read, and it will give me a slice of bytes. And my receive message will give me an error if something goes hideously wrong. But if I get either no error whatsoever when I'm reading bytes from this thing, which is a reader I wrap around that reader so I can use buffered I/O, then I will just take any crap off the end and send it back. The crap in this case being a carriage return. I know that everything that comes into here has a carriage return on the end because read bytes always gives you back with the carriage return. So I just drop the carriage return and the rest is the message. So now I have an advanced messaging protocol. Message loop, this is the bit that's actually doing what we care about. So for message loop, I just run forever, receiving messages on an I/O reader, and then doing some work with the string data that that message contained. Message loop doesn't care what that work is. This is part of the point. This is part of why I do this style of programming, where I pass in functions, higher-order programming. Because you just have to give it a function that knows what all of that is. This is boilerplate, that you only ever have to write the once. And once you've written it, that's it. That's just how you do it. In this particular case, if I don't get an error message when I receive my message, I just go through each of the numbers I get, and for each one of them, I do something. If I get an end of file, I give it a fair go. The last part of the message might be a bit effed up, but I'll give it a go. And if I do get a proper error, then obviously I'm just going to log it. So that's through that. I don't really know what to say about the pipe I/O stuff. I mean, pipes aren't specific to Unix anymore. There was a time when only Unix had pipes, but now Windows has pipes, and all kinds of other weird operating systems have pipes. I mean, because POSIX has pipes, and if you want to be POSIX compatible, you have to have pipes. A pipe consists basically of an input and output. You write on one end, you read from the other. You can read and write from both ends if you want to, and if you forget not to do that, you can end up with some very confusing bugs, because your process that did the writing might actually do the reading before the thing it was intending to read it got to read it. So you get your own message back, and you go, what the hell is that in my log? That was my experience for 2 days last week, when I completely forgot how I was supposed to be using pipes. because it doesn't matter how often you do this, you can still cock it up. One thing I want to make sure of, though, is when I've finished with pipes that I create, that they get closed. I would rather try this twice and get an error message turn up somewhere than not do this at all. Because sometimes operating systems decide, well, you haven't finished with that pipe yet, so perhaps I shouldn't get rid of this process. And if I'm not getting rid of this process, perhaps other processes that it created might hang around as well. And then you get basically garbage. I mean, yeah, zombies. You get zombies. And then this little thing here just means I can take however many handles for files and do stuff with them, but actually I'm only interested in these two up here. So I'm only ever passing in readers and writers for those two, the two endpoints for the two. I made that sound completely unintelligible. This is why people don't pay systems programmers anywhere near enough money. Now, this is the child. This is the one that wants to receive process IDs so that it can do something with them in the way of talking to other things. I really thought an hour would fit better for this. I'm so glad I put the other 4 examples in now. Right, so over here, I've decided it would be very nice if when I'm writing code that's looking up parent IDs, it actually gets the parent ID and gives me an actual process handle. So I can just say, for my parent, boom, do this. I think I've got an example. Right. All that is a wrapper for this. So for parent looks up a parent ID and then says for process. For process says, give me a process ID, and then give me a workload that needs to know about a process ID, and I will tie them together for you. And over here, as I said, on a Unix box, when I find a process, it doesn't mean it exists. So I have to send it a signal 0. Well, I can send it a signal anything, but a signal 0 doesn't do anything, so it's safest. And as a result, if I don't get an error when I do that, I do know it exists, so I can at least have a go at doing something. Otherwise, no such process exists. I don't know why it works that way. It's kind of weird. But anyway, for my parent, I know I'm going to want to handle some signals. Right? My parent's given me some information, and I'm going to want to handle some signals. And in this particular case, I'm just going to want to keep track of how many times I send this sig user off, boom. Or rather, I receive it, boom. So every time I get sig user 2, this counter increments, and I put that in as part of my log message to see how many times I've received it. Down here, every second for 5 seconds, I'm going to send a message saying hello, because I'm not confident that my parent is listening. So I'm going to brute force it. I could come up with something much more sophisticated, and it would take a lot more slides. And then, for every process ID my parent sends me, I'm going to go, well, for that process, I'd quite like to do some stuff. And I need to know my PID, because I'm going to send the signal, their PID, because no, my PID, their PID, that's their PID. Point is, processing can be very confusing after a while. So in this particular case, boom, 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 I send them a signal. Boom, boom. They get a sig user 2. They will do this in their process as it runs. And then over here, I've invented this stupid little thing here for each int, because what I'm getting in are strings. But I need to turn my strings into uint pointers, or rather uints. And then I need to fake them. Oh no, that's a later example. In this one, I just have to turn them into integers. I've got another example further along where I have to turn them into uints, which is slightly more annoying, because there isn't just a, A to U. You have to actually properly format them and stuff. We'll get to that. Maybe. I've only got 8 minutes and 22 seconds. Right. Which would you rather see? Named pipes, which are something that lives in the operating system and has a name, or who wants to see how to do horrible stuff directly with syscalls?
Horrible stuff.
Right. You're my kind of audience. We'll skip past that. It's in the slide deck. Everybody can go and read it. Where do we get to? Name pipes. Oh, yeah. So let's start with CGO, because obviously the reason everybody's turned up is the 8 minutes in which I talk about CGO. I don't actually use it very much because nobody should use it very much. If you find yourself having to rely on putting lots of C code into a Go program, you're probably doing something wrong unless you're wrapping something like a database library or something. But on the other hand, you can put C code literally inside Go code as a comment. Import this sudo package C, and then reference your C code in your Go code. Now, that's kind of neat. I do like that. I'm accessing some things over here that aren't named over there, though. Sempost, semclose, semunlink. What's this? So this example is about semaphores. And a semaphore is something that lives in the operating system that I can grab a lock. I can increment it, or I can decrement it. And I can effectively use it as a locking mechanism. I can wait until it's clear before I progress. I've done a beautiful job of butchering that idea. So, in this particular program, what we've literally written is a Go program that talks directly to the underlying operating system's functions for handling a semaphore. So why have I got this? Why can't I just call semopen? Well, semopen, unfortunately, exists in two different forms. And CGO does not cope with variadic C functions. As far as it's concerned, a C function has a fixed number of parameters. That's it. One set fixed number of parameters. It shall have no more. But unfortunately, you often have libraries that say that's not true. So to get around that, in your C code, you write a little wrapper that only takes the number of parameters you want. And to be honest, all I want on this one is I just want a name. Although that's slightly complicated because I want a name in a string that C understands. Now, C considers any string of bytes with a null at the end, if it happens to be assigned to a car pointer, to be a string. Go is pretty determined on what a string is. I don't know if it's still actually got a string header, because I haven't played with reflection in a while, but it used to have a string header that would tell you exactly where in memory it lived, how many bytes long it was, and it doesn't care about nulls at the end, they're part of the string. Which is good, because the operating system considers nulls part of the string if you send a string into a syscall, which is always a bit of a confusion. So in this particular case, I've wrapped this up like this, and then I've used a C string, because we've got some type conversions that we can use. I take a command line parameter, and I go, that's the name of the damn semaphore I'm going to create. But because of that, I have to free it. But what I actually have to free is a pointer. And it's an unsafe pointer. So if you ever find yourself using unsafe encode, don't, unless you have to. Do not do what I did for several years and write this stuff for fun, only write it for profit. Right? So I'm going to skip on from that. Because what we can, oops, now what's different there? Something changed behind my back, didn't it? Boom, ba, 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 ba. Of course. This is I've called this 9 create. So this is the program I run first, and it will create a semaphore. This is 9 use. This is the program I run second, and it will use the semaphore. That's not really how semaphores should be used. It's just convenient for slides. But as you can see, we end up with the same code, but we're doing a slightly different thing. They're going to ping pong, and I'm going to do this quickly in the terminal. God, I'll be glad when my eyesight just decides to settle on one distance. Right. Oh, we left you hanging. Now. And it needs helpers.go. It takes a parameter, doesn't it? Yeah, so let's call that 09.sem. Boop. That's the creating half, and I'm going to lift that out. Oh, no, I can't use that one. Right. So, as you'll see over here, when I've expanded the text up a bit, as you'll see over here, it creates a semaphore, it opens it, it locks it, and then it decides it's finished with it. So if we run that one again, and then we come over into this terminal here, Now what I've got to do is get the oh god, get the timing right. And of course, make sure that they're using the same semaphore name. Otherwise, they won't marry up. Right, off you go. And then off you go. Oh, that's last-minute slide edits for you. All right, we'll ignore that. The point is, what will happen is both of their logs will show that as one releases the lock, the other one can acquire the lock. And there's a 10-second gap, so that it's very obvious in the log. So we'll go back to that. Boom. There isn't really a lot else to say about what the program actually does, because it's designed to be stupidly simple. But, right, that's back that way, that's that way. So, all right. Because of the way in which I've laid this set of examples out, they're all stored in the same directory. There is one interesting little wrinkle. If I try to just do a go build, it gets very upset and says, I know nothing about any of this CGO stuff that you're doing. Unless I move it all into a subdirectory. Because if I go, right, this is really weird. If I use go build and I give it the name of some Go files on the command line that it should build with, it won't associate them with any C files that you've got in the directory. And I've moved the C stuff off into its own files. But if there's only, if you just run go build or go run with what's actually in the directory, and there's nothing else there, it does it fine. It took me about 5 hours to figure that one out. I kept thinking, what the fuck is going wrong? It worked fine there. But so there's two pieces of code that both live in their own separate subdirectories, and it's literally so that you can actually get CGO to work properly with them. Right. Now, we finished with CGO. This is the very last example. How is it? I've got an hour and I'm still going to be 3 minutes over. I seem to know how to write 3 minutes too long at all. Right. So in this particular case, we're going to do something a little bit more funky, because CGO is us actually relying on C to do the job for us. C knows how to link to various libraries that do all of this sanely. I can put little platform-specific defines in. I can use build tag support in my Go program. But what we're about to do is truly go down the rabbit hole of madness. So I'm going to skip on. Welcome to my Darwin-specific semaphore wrapper, purely using Syscall. Now, I've moved on from using the standard package Syscall. I'm now using xsys Unix. People keep assuring me this is where everything will turn up, but nothing I want ever seems to turn up in it, so I don't know who it's for. But in this particular case, I've decided I've got particular requirements about how I want to write my code. And this is almost where I'd go, because what I'd actually do is create a map that's a jump table where I would give it a string, and it would give me back the function that actually does that work, and then it's a lot neater in line. But as nobody else metaprograms in Go, I don't expect anybody else to do that. Right. That's just a Rubyist thing. We can't see a thing and not go, could I meta that to death? Right? And Go will allow you to do it, but you might not want to see the code. Now, in this particular case, I've got 6 functions that I can do on a semaphore. I can open it, I can close it, I can unlink it, I can wait on it, I can try to wait on it, and it will give me a different error. And then I can post to it, which increases the count on it, right? It doesn't really matter how that works. It's a MacGuffin. The MacGuffin has got 6 arms, and I can tickle any one of them I want. The open is the most complex bit. This requires that we send a Syscall 6. But we don't have 6 parameters. We have 1, 2, 3, 4. Well, actually, we have 4 parameters that we want to send through. We have an opcode, that's 5. And then we've got 2 parameters we don't give an F about. And that's why it's called Syscall 6, because it takes 7 parameters. Right. So I love Unix naming. There's so much Unix naming in this half of Go. It's brilliant. Right. We're doing some error handling, because error codes that come out of Syscalls can be a little abstract, but we do actually get a C-style error number. Now, if I was going to do this seriously, I would put some constants up here, and I'd have things like einval and so forth, and I'd give them a value. And then I'd be able to check against those when the errors come through, and I'd be able to do different things on different kinds of errors, because some kernel calls have quite a wide selections of reasons why they'll go wrong. These numbers here, these are incredibly operating system specific. Now, if we were doing this on Windows, which in principle we can, they're not just operating specific, system specific in the sense of Windows. Different versions of Windows have different syscall numbers. And Microsoft strongly discourages you from ever using them. And when I say different versions, I mean different revisions. So Windows 2000 with Surface Pack 2 might have some different kernel numbers. I guess he's going to try and rip me off the stage in a second. All right. That code is all fun. Go play with it. There's lots of different system calls you will find. Every operating system has a header file that's got all the numbers in. And then you can plug stuff in. So I have a little book. It doesn't have any of this stuff in yet. That's another set of unwritten chapters. But it's on LeanPub, so you can go and buy it now and make me feel happy because I can buy beer. This set of books down here is a very good way to get started in all this malarkey. These two over here are very sensible. I just bought myself a new copy of this because I've moved house and the old copy has gone missing in the house move. And I was really pleased to discover I could get one for £6 now because I paid a hell of a lot more for that back in the day. There are, as far as I can tell, only 2 books that are published on systems programming in Go. And that's both of these from Pact. I've browsed through them. They're not bad. There's bits I would have preferred covered that aren't, and others that I probably wouldn't bother with. I have a slide share. It's full of mad talks. There's a companion to this one that I gave last week for RubyConf South Africa, which is at present a virtual conference, which is everything you need to know about networking and crypto. If you would like to know more about this and have enough money to afford it, I highly recommend coming to Florence in October and watching me give this as a 3-hour workshop. I think I can add maybe 50% more content if I'm going to do that. And then finally, there is a GitHub that is full of all of this stuff. And if you were looking at the bottom of the slides, you will notice there is a link to that GitHub there. Thank you very much. I seem to have gone over by red. Thank you.